Assalamualaikum warahmatullahi wabarakatuh. So this is my final year project title, which is Iot-Integrated Handheld Optical Device for Abdominal Heart Rate and Oxygen Saturation Measurement. So my name is Nifilza binti Wan Baharudin and my supervisor is Professor Madiati S. Dr. Nur Anida binti Jumadi.
Let's go to our problem statement, which is normally pulse oximeter are used on finger and ears, but for some patients like premature babies or people with injuries, it's hard to use those areas. So I developed a device that can take readings from the abdomen to help in those situations. Next is objective. So for the first one is to design and develop an IoT-based optical device for abdominal pulse monitoring. Next is to measure the heart rate and SpO2 on the abdominal. And the last one is to evaluate the functionality performance on developed device on the abdomen. Scope study of this project is the prototype development and IoT integration using MAX 30102, ESP32 and Blink. The next one is heart rate and SpO2 algorithm using Arduino IDE software to write the coding. And the last one is performance evaluations. Benchmarking was done with a pulse oximeter tested at 9 abdominal region in both sitting and supine position to observe the consistency of heart rate and SpO2 measurement across different body posture and locations. Let's go through the methodology. This methodology represents the procedure and technique used in this project. So we have the project flowchart, and for the first one is start the project, which is build the IoT PPG system using ESP32. If it's not working, we need to fix the code. The second one is to create a casing for the sensor, which is for the abdomen area. If it's not working, troubleshoot. The third one is test if the system works properly, which is compare the fingertip pulse oximeter. If it's not accurate, troubleshoot. And the last one is write the report, which is comparison, result and the suggestion, and end. System block diagram. So we have the MAX 30102 sensor read the heart rate and SpO2 level, and then it goes to the ASP32, which is the process the data from the sensor, and then we have output, which is the OLED display to show the result from the OLED I2C, and then it sent to the IoT platform to send the data online, and then you can view it from your phone or tablet, the result. Flowchart heart rate and SpO2. So we have start, which is the begin the program, and then it goes to declare variables to set up the BPM and SpO2 and signal buffer, and then sensor measure signal, sensor read light signal from the body, and then check if the reading are valid. If are HR and SpO2 okay, if yes, we need to continue. If no, measure again, and then display the initial value, show the raw BPM and SpO2 reading. Then process the signal, use the algorithm to calculate accurate value, and then output final result, which is to show the final BPM and SpO2, and the last one is end, finish or repeat the continuous data. This slide showing the result of finalized prototype called Tummy Pulse. If you can see in the slide, we have the OLED I2C and also the button on off. At the right side on the Tummy Pulse, you can see the ESP32 port, and then the lithium battery charger port, and at the back of the prototype you can see that MAX 30102 sensor. This is the Blink interface from our project called Tummy Pulse 1. On the left side you can see the BPM, which is show the heart rate. On the right side is the SpO2 showing the oxygen level in the blood. So both values are taken from the tummy area using MAX 30102 sensor, and they are sent live to the Blink app through the ESP port. Okay, so this slide show the table of the BMI value for all 6 subjects in the study. So we have 4 female and 2 male. So we include the different BMI categories such as underweight, normal, overweight, and also obese, to see how the body types affect the reading. This slide show how the data was collected in 2 body position, and for the first one we have the sitting position, and the second one is the supine position. This aim to compare how body posture affect the sensor reading. So this table showing the measurement and frequency analysis of the abdominal region for heart rate. So I test 6 subjects in 2 positions, which is sitting and supine position. For each region from R1 till R9, so the bold value indicates the most similar value to the benchmarking of the pulse oximeter. So in this study, the value is considered similar if the difference is less than or equal to 6 ppm. Then from both tables, the frequency analysis was done by counting the number of times the same value appeared in each abdominal region. For sitting and supine position, it can be seen that R5 and R2 had the similar result compared to the pulse oximeter. From the analysis, the findings show the most optimal region in sitting position is region 5, followed by region 2 and region 1, 3 and 4. Meanwhile, for the supine position, the most optimal region is the region 2, followed by region 5 and 6. Slideshow showing the measurement and frequency analysis of the abdominal region for SpO2. This table is similar to the heart rate. Okay, so for sitting and supine position for SpO2 values, it can be seen that R2 and R5 had the most similar result compared to the pulse oximeter. This is the frequency analysis of the almost similar abdominal region for SpO2 with the fingertip oximeter observed in sitting and supine position. The findings table show that the most optimal region in sitting position is region 2, followed by region 5 and region 7 and 9. Meanwhile, the most optimal region in supine position is region 2 and 5, followed by region 4. Let's go through for percentage error formula to evaluate the accuracy of the sensor readings compared to the pulse oximeter, which is the reference value. So PE equal to reference value minus by the sensor value divided by reference value times by 100%. This table shows how close the heart rate reading from the abdomen area to the fingertip oximeter when the subjects are in sitting and supine position. The row represents 6 different subjects with different body types. We have the underweight, normal, overweight, and obese. The normal column R1 to R9 represent the different region on the abdomen where the sensor was placed. The number of percentage error value, lower values mean more accurate reading, which is closer to the fingertip reading. From the sitting position table, we can see that R2 and R5 has the most lowest percentage, which is the best region for heart rate. Meanwhile, R7, 8 and 9 had the highest PE error, which is not good. For supine position, we can see that R2 gave the lowest percentage error for all 6 subjects with value less than 6%, showing that this region is the most accurate for heart rate readings, followed by R5 and R6. Slideshow showing the measurement and frequency analysis of the abdominal region for SpO2. This table is similar to the heart rate. Okay, so for sitting and supine position for SpO2 values, it can be seen that R2 and R5 had the most similar result compared to the pulse oximeter. From the experiment, we can conclude that region 2 and 5 are the most suitable for measuring both HR and SpO2 in the sitting position due to better sensor contact and arterial proximity. And then lower abdominal regions like R8 and R9 show the weaker signal quality, especially among underweight and obese subjects, likely due to issue thickness and movement. In the conclusion, this project successfully developed a handheld IoT-based optical device using the MAX 30102 sensor and ESP32 to measure heart rate and SpO2 from various abdominal regions. However, the readings obtained did not consistently match the fingertips measurement, indicating that the abdominal region may not provide the most accurate value for precise medical analysis. Future recommendation: improve the algorithm to get the accurate and stable heart rate and SpO2. Next is to using multiple sensor allows data to be compared and validated, which may increase the accuracy and reliability of the readings. And the last one is to upgrade the IoT interface. Limitation of study. The readings from the abdominal area are not always stable because of the signal are weaker than at their fingertips. This can cause the heart rate and expected data to be missing or inaccurate. And the small body movements or changes in position can also affect the sensor, making the sensor quality worse. Since the system doesn't use AI, it only allows fixed rules in the code and cannot adjust to different user or situation, which limits to its performance. So this slideshow showing how to use the prototype. So for the first step, we need to turn on the device by switching the red button on the on position and wait for the device to connect to the Wi-Fi and show the tummy pulse ready on the screen. And then after it is connected, the screen will appear the tummy pulse ready, which means the device is ready to be used. Once the message appears, place the device gently on the tummy area to detect the SpO2 and heart rate.
Nak tanya? Okay.